So thanks again, everyone, for joining. My name is Dan Yeaw. I'm a systems engineering and functional safety manager at Ford Motor Company. And I'm going to be giving a talk on network graphs and the semantic web with Python. First of all, I'm going to give kind of some introductory material on like what are network graphs, what are nodes and edges, what is the semantic web, and then we'll do some live demos of how you make use of that. And I'll be using Jupyter notebooks in Python to show some of the libraries. Once again, if anyone has any questions while we go, feel free to ask. You can either put your questions in chat or come off mute is fine as well. So one of the things I'm going to talk about is kind of this basis for a digital thread. So we want to be able to connect information together to create this like universal access to data. Often we kind of have separate tools, separate databases, separate websites that aren't connected. And we often spend a lot of time looking for the information that we need to do our jobs or complete our day-to-day work or searching for things, right? And I find this especially like inside of businesses. There's like, you have to send emails out or look on wiki pages trying to find the information you need instead of just being able to query information that exists and find answers to the questions you have. So data needs to be distributed across computers in order to access that data where it's created and stored. So often we use many different types of applications to create, whether it's like engineering or finance data or whatever it is, the data gets created in many places, and then we need that data distributed from where it was created so we all have access to it. Although we could place restrictions on who and what can create the data, our ideal goal for this kind of digital thread or semantic web is anyone can say anything about any topic. And then we want to be able to query that data to get information that we're looking for. And so that's kind of, we're going to use that AAA portion for the semantic web to discuss, hey, how can we actually achieve that where we can connect this information and really anyone can talk about what they know about a topic. So one of the things we're going to talk about is called RDF, which is the Resource Description Framework. So this is from the World Wide Web Consortium, W3C. They have a specification, and this is what this, what's it called, the semantic web was formed from. And this is a form from a metadata data model and was first published in 2004. So it's not a new thing. It's been around for a little while. And so it's this general method for describing or modeling of information that is implemented in web resources. And you can see here, this is actually what RDF looks like. It's in XML, and it has these things called URIs, which are just a certain type of URL like you'd have on a website. And then you just, I guess in this, there's a different tag. So for example, this is an RDF description, and it's saying, hey, this resource, this Poke API has a title and an author. And this is a single piece of information about the RDF. And I'll go in a little bit more like how this RDF is formed so that we can access data. So the difference between like a semantic web and maybe what we're used to for the World Wide Web is you create kind of these graphs of information and then connect that information together through things called nodes and edges. And we'll talk more about that. And I'm also going to use Pokémon to describe a lot of things today. So we'll have a little bit of fun with that. So if you want to represent Pokémon as data, you might have a table. So this is a table of a bunch of species. So you have Bulbasaur and Ivysaur and Charmander and Charizard. And so each row is an item, and each column is a property of those items. So for example, we have the height and the weight and the base experience, and those are all kind of properties of them. And so it's in this table form, and I'm sure everyone's kind of used to seeing data in a form like that. Now, if we wanted to distribute the data, you could do it a couple ways. You could distribute the data row by row. And in this case, we could say, hey, server 1 has some of the data. So they have the first 2 rows. Another server has the second 2 rows. And the last one has the last 2. And in order to do this, it requires a common schema to coordinate across the servers. And what I mean by that is you would have to coordinate across the servers which column represents what type of data. Otherwise, if you didn't have a common schema, then one column on one server might not represent the same type of data on another server. So that would be if you were trying to distribute data row by row. You could also do it column by column. So you could say, hey, this one server has the species and maybe the IDs. Another server has a base experience, and another server handles the height and weight. If you want to distribute data by columns, then you have to have some type of reference entities to coordinate across them. So in other words, you have to have a reference to some type of row or ID to know that this top row for each table represents the same thing across the servers. So the third way you could do this is you could distribute data cell by cell. So you could split it up and say server 1 has 1 cell, Charmander. Server 2 has 1 cell, this with ID 1 and height 7. And server 3 has just this 1 240 base experience. And you would distribute all the cells across the servers. So the disadvantage of this is it carries the cost of both. So you need both a common understanding of what the reference is and a common understanding of what the columns are. But what's nice about this is it, once again, allows anyone to say anything, anything about any topic. So now any server can say, if it knows what the ID is and the column name, it can make a statement like, hey, ID 4 corresponds to Charmander, or ID 6 has a base experience of 240. So when you're working on that server, you could create information about, I guess, any of the Pokémon, and using any of the different properties to create that data. So in order to do that, each cell has 3 values. So there's a global reference for the row, a global reference for the column, and the value in the cell. This is really the basics of RDF, and it's called a triple because there's 3 pieces of information: the reference to the row, the column, and the actual value in the cell. RDF does use something called grammar names to represent this. And so instead of calling it column, row, column, and value in the cell, it's called a subject, predicate, and object. So the subject is this reference to the row, the predicate is the reference to the column, and the cell value is called the object. Subject, predicate, object is what a triple is. So here's a sample of a triple. So EV, that's one of the characters, can evolve into either Flareon or Umbreon. And this is kind of what this subject, predicate, object looks like. So a character EV evolves to, that's the predicate, character Umbreon, or EV evolves to character Flareon. And notice, and we'll talk about this more in a second, kind of the subject is this starting place. The predicate is on the line that goes to another piece of information, and that's called the object. So you kind of see this graph forming between the subject, the predicate, and the object. Is there any questions so far from anyone? And I'll start to get into why this is useful, I guess. We'll see that in a second.
The arrows are one directional right here.
That's right.
So the subject is always at the start of the arrow.
Yeah, that's right, Charlie. Yep.
Okay, thanks.
Okay.
So if you have it going back, can they evolve back? Then I guess it reflects back.
Yeah, so the question is could a Pokemon evolve back? So
like cycle back and forth. Yeah.
yeah, so I think in this case, I'm not an expert in Pokemon, but I don't think they de-evolve. But
Okay.
if they could de-evolve, then maybe you'd want a different, and you wanted to add an arrow back, maybe you'd use a different predicate for that. Maybe, yeah, maybe it would be de-evolve or something like that. And then you could have relationships back, but it would have another arrow, and that would be a new triple that would say, you know, Flareon de-evolves to Eevee.
Okay. Okay. Thanks.
And so it's always those, yeah, subject, predicate, object for
Sorry,
every kind of piece of information.
Can I say something?
Sure.
Okay. I had some experience a few years ago about this.
Mhm.
This is related with semiotics. You know, if the relationship is reflexive or not depends on the semantic of the verbal form. For example, if I say quads are related to embryon, that's reflexive, because if A is relating to B, that implies that B is related to A.
Mhm.
Sorry, but there are many verbal forms that are not reflexive. That depends on the semantic of the form. For example, if I say Mary is the wife of Tom, Tom is not the wife of Mary, never.
Yep.
So there are certain semantic that define the antonym of the verbal form. For example, I can define that is wife of is the antonym of is the husband of. So if I say Mary is the wife of Tom, that implies that Tom is the husband of Mary.
Yeah, so that's a good point. So what I'm kind of showing here of like, these are explicit triples or, you know, RDFs that we're creating, but you could also have implicit ones based on semantic rules. So as you mentioned, if someone is the wife of someone else, then the opposite way is probably that person is the husband of the other person, right? And you can create implicit rules like that that automatically create more pieces of information based on kind of, yeah, those semantics. So yeah, thanks for bringing that up. I think that's a good point.
So Dan, you subtly put in something which can't be done in row column format, right? You've got a multi-valued target there for evolves.
Yep. Yep, that's right. And that's kind of, I guess that's where we're getting into network graphs, which can't really be, and why this is a little bit different than everyone, you know, thinking of the standard way of representing things and, you know, tables or traditional databases, is they are in like these kind of columns and rows, but we're going to talk about a different way to represent data. And this is using something called a network graph. And there's also graph databases that you can use to represent data in this form as well. So what this network graph is it has nodes and then lines connecting the nodes called edges. And the edges can also have weights. And what that means is, for example, if our nodes were airports, right? So we have map of all the airports in the country. Your edges might be, say, the distance between the airports. And so that distance would be the weight on that edge. And not all network graphs have, I guess, weights assigned to the edges, right? But that is a possibility depending on what type of like network graph you're creating.
I have a question.
Yep.
So like, what would the weight like kind of mean in this situation? So like, You said it's the distance, so does it like mean the data is like harder to access, or is it like one becomes more of a default value, or what does it exactly mean if it has a greater or smaller weight on the edge?
So it just depends on what type of data it is. So so if you were looking for using a network graph to figure out the, I don't know, shortest time to get from one city to another, I'm using flight information, then maybe your weight might be flight time or might be distance or something like that. So it kind of depends on what you care about and then how you would use that weight information to I guess get the, make decisions with the information you have. So
Okay, so
Dan, hello.
Yep, go ahead.
Okay. Okay, listen, the distance is related maybe with how you made inference. One simple example is if I have a meronomy, is a containing a part of relationship between physical places, for example, I can say Lansing is part of Michigan, Michigan is part of the United States. So I can make the inference that Lansing is part of the United States.
Yep.
But the semantic distance between Lansing and Michigan and the US is inferior than the distance between Lansing and the US, for example.
Yep.
Again, that the concept of distance depends of the semantic of the verbal form. In this case, part of. Okay.
Yep. Yeah, thanks for sharing that. Yeah, so it depends on the semantics. Okay, I'm going to keep going. So this is like a graph display of triples, just as we saw a graph a second ago. So if Bulbasaur is number 1, so it's got a name Bulbasaur, so that could be a relationship. It's got height, weight, base experience, just like we saw on the table. And you could also make relationships between them, like Bulbasaur evolves to Ivysaur and Ivysaur evolves to Venusaur, right? And once again, in the graph form, the subject and objects, this would be the subject, this is the object, are nodes, and the predicates are the lines. So in that case, the evolves to would be the edge or the line. So if we want to distribute data across multiple computers or sources, we must merge it back together. So we need to know when information on one computer or one source is the same as information on another source. And so what we would do is form the graph of the triples, and then we need to answer the question, when is a node on one graph the same as a node in another graph? So for example, we have Charmander is sourced from this object, this URI, this object called this API here for Poke API, and Charmeleon is sourced from this Pokemon database, and Charizard is sourced from this Pokemon Pokédex, right? So they're all different sources, but we need to understand when Charmander or Charmeleon is on one database, that it is the same exact Charmander or Charmeleon on another one. So we use unique IDs. So uniform resource identifiers, URIs, is how the web shows things are unique. One example of what people are used to seeing for a uniform resource identifier, a special type of that is called a uniform resource locator. So probably everyone's familiar with that. So you would type in, say, michiganpython.org to go to our meetup. So that's, the URL is a special type of URI. And so RDF also uses URIs to make information unique. So Poke API has its own URI, or the Pokédex has its own URI, for example. And so these URIs become a global identifier and they're unique. So there wouldn't be two, just like you can't have two websites with the same URL, you can't have two pieces of information with the same URIs that aren't different or something. So for example, yeah, this Poke API for Bulbasaur, you could say that evolves to whatever is an ID 2 of that Poke API, or Bulbasaur name is Bulbasaur, or Bulbasaur's type is a Pokemon. And you could also say this ID 1 is the same as, and this is another unique identifier for same as that you can make use of, is the same as the Bulbasaur in DBpedia, which would be another reference. So this is where you can start connecting those nodes to say that this node in this one piece of information is actually the same node in this other information. You can also define custom types. So we can say something like Pokédex gender. So we have a gender for our Pokemon. And some of these things like RDF is these common ontology that you can make use of. They've already defined what a type is. And you can say like, well, this gender is a type of property on our Pokemon. And so the RDF namespace provides this agreed to base dictionary that you can make use of when defining your RDFs. So I'm going to talk about some of the libraries we can use for Python for this. So there's rdflib. So this is a library that allows you to parse and serialize and store and graph RDF. There's also something if you're I know earlier someone mentioned like, hey, I do a lot of SQL. So SQL is a way from parsing information from a database. There's another language called Sparkle, which allows you to collect information from a graph database and run a query to say, hey, I want to know all the Pokemon that are named Bulbasaur in the database and get that information. We're also going to be making use of a library called NetworkX. So this is network analysis in Python. So this allows you to create, manipulate, and study the structure, dynamics, and functions of complex networks. And once again, these networks are built up of these nodes and edges. So NetworkX is a library specifically for that. And finally, we're going to make use of something called pyviz. And this allows you to create and visualize interactive network graphs with Python. And there also is a Python or a set of Python visualization tools called pyviz, and I always mix these up. So this is not the one with a Z, it's the one with a S. So just be careful there because I've made that mistake a whole bunch of times. Okay, so that was kind of like the background information. So once again, we talked about, kind of connecting information in a semantic web. And we want to connect it using this triples so that anyone can say anything about any subject. And now we're going to kind of show in Python, how would you create these nodes and edges? How would you make use of RDF and create RDF? And also then how would you graph and visualize that information? Is there any questions before we move on to the demo?
Yeah, Dan, maybe you said this, but just trying to get the language right. If a subject is an object and an object is a subject, is that the same thing as saying it's a node? So that those two sentences are the same. Something is a node means that it is both a subject and an object. Is that correct?
So let's, I don't know, do we have a picture of a graph we could go to?
Yeah, maybe the one just.
So this node right here is only a subject and it's not an object because it starts here for a subject of this, and then this is the predicate and then the object. So it is only the subject.
I see. Okay.
And then this one is only an object because it has a subject predicate object and a subject predicate object.
Okay.
And then
that
this
makes
one
sense.
is
Okay.
both, right? Because it has an
thank
arrow
you.
going in and out. Yep.
Yeah, that makes sense. Thank you.
Any other questions before moving on?
I think that would be the case of a self loop that the node is also as target. So the edge would come back on itself.
We're getting some feedback. So yeah, if an edge came back on itself, so you could say, I guess it's possible that a node could be both a subject and an object and has some type of relationship to itself. That's definitely possible. I don't have a good example in my head right now on like when you would do that, but you could definitely have a relationship between, yeah, a common node that's the subject and the object. I think that was maybe your point. So thanks for bringing that up. Did anyone else have any questions or comments?
Yeah, so I guess with the anybody can say anything part,
Yep.
How does like discoverability of like sources of information work? Or is that out of scope?
So yeah, right now, I think our RDF is primarily being used, and yep, I think you went back on mute, Brian. I was getting some echo. So right now there is like RDF on the internet, so you can go find RDF and make use of it. So for example, there was that like DBpedia, which is kind of like Wikipedia, but it's all in semantic web or RDF. I think it would either be created by people manually making those connections, like, hey, this picture here that I found in this resource is actually a picture of Bulbasaur or something like that. So someone manually creating that linkage and saying this is the same. Or I guess you could, once again, create rules and infer relationships and say, hey, if I find any object out there, with name Bulbasaur, maybe then I would assume that it's the same thing. So I think you can either like infer relationships and done automatically, or people creating manual relationships by saying, hey, this Bulbasaur resource is actually more information over here in this subject and stuff like that. So I think it's very similar how you would normally I guess get information on the internet. Is just in a different form. So you either create links to resources that you say, hey, for more information about this, go to this link over here. Or, like search engines and other things make finding information easier and kind of automatically create links. I think it's very similar for the semantic web, using those like kind of two cases. Either you're creating implicit relationships or someone is explicitly saying they're the same thing.
Makes sense.
Okay, any other questions, anyone? Okay, so I think everyone can see we have a Jupyter Lab notebook open. So we're going to go through a couple things in Jupyter Lab and kind of discuss how we would do kind of use of the RDF and then start once again graphing things and showing some of the stuff. So if we want to create a new Pokemon, so once again, we're using this rdflib library. So you can pip install rdflib. I've already installed that in my Jupyter notebook for use or in my content environment. So we are going to import these different things for rdflib and kind of talk about those. So the main part of rdflib is creating this graph. So we talked about rdflib allows us to create these kind of network graphs of RDF. And so a lot of the things we do is based on creating an instance of a graph. So we imported rdflib graph, create an instance, and then it has some of these built-in namespaces that we talked about. So there's a namespace for RDF called friend of a friend or FOAF. And so that's a ontology describing people. So we're going to go ahead and make use of FOAF. So we did this bind of FOAF to our graph. And then we're going to define a new namespace. And so this is us saying, hey, we're making use of this information at michiganpython.org/Pokédex. That's going to be our Pokemon information resource. And we create this namespace and say, this is the namespace we're going to use. And then every time we type in Pokédex, it knows where we mean this namespace that we're making use of. And we can also use the dot operator on it. So we say Pokédex.Pikachu means the same as typing out all this URL and putting /Pikachu on the end, right? So we're using this namespace and referring to as one character in it. So pretend we created a new Pokemon called Kadazar. That's not a real Pokemon, but if we are creating a new one, if this isn't in a resource yet, we can still use it in an RDF. And we use this B node to create one, and it actually generates a new global unique identifier. And so we're still making use of this, even though it hasn't been like put in the official Pokédex yet. And so we can also make use of things called literals, and that was imported up here as well. So we used a string literal for RDF named Pikachu, and we used a number literal 24 for the age. And then we're actually adding some RDFs directly. And each, once again, this RDF's a triple. And so you do G, which is our graph dot add, and then you pass in what you want in the triple. So in this case, we say Pikachu is once again, we're using the RDF namespace that's already defined. RDF.type is a type of Pokédex Pokemon. So we said Pikachu is a type of Pokemon. Pikachu, friend of friend ontology again, has a name. And Pikachu's name is the name we define, the string literal called Pikachu. Pikachu has an age of our string literal 24, and Pikachu knows Kadazar, which was that new Pokemon we created. And Kadazar is a type Pokemon, and Kadazar has a name, string literal Kadazar. So then what we're going to do is then serialize that, which means take these RDF statements and convert them back into a format we could say save and give to other people. And we're going to use a default of that, which is called Turtle, which stands for Terse RDF Triple Language. And it's kind of a abbreviated form that you can save an RDF in. So we can go ahead and like run. We can go ahead and run this. And you can see here that this is what the turtle language looks like. Remember those namespaces that are built into rdflib. One is this FOAF, and one we have just a normal like XML schema. So it's saying anywhere FOAF or XSD is used, you can just replace it in here. And so all it's doing is writing our triples that we had up here. Remember we said Pikachu is a type of Pokemon. So down here in Turtle, it says Pikachu, and you notice the URI is in front of it. That's the full unique identifier. And you say Pikachu is a Pokemon and has age 24 and knows a Pokemon named Kadazar, and its name is Pikachu. And so you could now save this as a .ttl file. That's what the turtle is. And you can, put it on the internet or connect it to another data source. And so that's how you would use rdflib to create, RDF. Is there any questions about that?
Dan, I have a question, and if you went over this, I apologize. I'm not familiar with the term literal. Is this just specific to this library, or so like when I've used Python, if I was going to do name, it would just be name equal, you do the quotations and call it that. So could you explain a little bit more about why we're using literal here?
Yeah, that's just part of RDF. So it describes things like a string or a number as a literal. So it's just part of the RDF language, and in order to make use of it in the RDF, even though that's not what you would normally have in just normal Python, we have to like create this literal called Pikachu. Same,
you.
yeah, no problem. Thanks for the question, Amanda. Any other questions, anyone? Okay, so now we could actually load an RDF file, and there's a format called n-triples format. And if we, let's go look at this demo.nt file. So you can see this n-triples format has the subject, in this case, that's me, Dan. We have the, once again, this is the full URI for the RDF syntax of a type. And then this is the full FOAF syntax for a person. So all this says is Dan is a type of person. And then it ends each triple with a period at the end. And Dan says, hello world. And then you end up with a period. So that's what the demo n-triples format looks like. So what we're going to do, and all this import is importing something called pretty print, which will make our print statement look a little nicer for the formatting. And so what we're going to do is take that path, the demo.nt, which is the n-triples format. We're going to create a graph. We're going to parse that file, and rdflib knows how to do that. We can print how big the file is. There was two statements, so we expect the length of it would be 2. And then for each statement, we're going to print it. So each statement in the graph, print the statement. So we'll see what that does. So once again, it loaded that into RDF, into the RDF lib, into a graph. It parsed it, and then we printed it. So you can see RDF lib has this term called then a URI ref, which is its form of a URI, this uniform resource indicator, which allows it to say, hey, this is some unique, and it looks like there's a typo, 2 S's on HTTPS, but michigan.org Dan says hello world, and the other one is Dan is a type person. So you can see how RDF lib read in the file and then is making use of it. And we can do other more exciting things with RDF lib, and I can show that. So that's just like a basic example of reading a file. So I went on the internet and got an actual Pokédex in RDF. And if you're not familiar with Pokemon and Pokédex is kind of its dictionary of all the Pokemon. And you can see this file is very, very big. Right? It took Jupyter a little while to load it. And so its URI is pokédex.dataincubator.org. And so at the beginning, it's saying this URI has a description and provides a description, or its title is Pokédex data. And if we scroll down here to maybe like an actual Pokemon, so Pokemon 101, you can look at things like Pokemon 101 is of label Electrode, so that's its name, or Pokemon 101 is of type Pokemon. So it's very similar to what we saw before, except this is a huge, huge n-triples file with a full Pokédex in it. So we're gonna load that in instead because it's a little bit more exciting than that hello world one. So once again, it's the same thing. Pokédex.nt.n-triples will create a graph and parse it, and then we'll print out how big this is. And it's going to take it just a second because it's got to parse it all. So there's 26,562 triples, which is quite a lot. So we've loaded in the triples. So now we can do things with RDF lib. So let's create a subgraph. So we want to just, since this has 26,000 triples, let's get just like one triple out of it that we're interested in or something like that. So we can use Python to do that. So we created a subgraph. We said Bulbasaur, the name is the URI ref of Pokédex.dataincubator.org Pokemon 1. So that was the first Pokemon ID, and we just call it Bulbasaur so we don't have to type in this URI ref each time. And so we say for SPO, which stands for subject, predicate, object in g.triples. And then we can use this g.triples to say we are looking for any subjects of Bulbasaur, which would have this whole URI, and we're looking for any that have a label. And then the none here means we don't care what the object is. So we have set what we want the subject and the predicate to be, and then we're looking for any object. And if we wanted to, and we can show that, you could set the predicate to none and look for any triples related to Bulbasaur at all. And then at the end, we're just going to print using the F string format, the subject, predicate, and object. And it found it right away. So there's, it looked through those 26,000 triples and said, hey, Bulbasaur is here, that Pokemon won, and it has a label of Bulbasaur. Not that exciting, but if you wanted to see all of the things related to Bulbasaur, we could get rid of the label here and just say they're both none. And now it's going to find all the information about Bulbasaur. So these are all, yeah, you can see there's like multiple languages that are defined. Yeah, effort and special attack. All this information about Bulbasaur was in this Pokédex. So you can look at it all. So you can see how you can use Python to filter out the information or look for stuff in the triples that you're interested in. Does anyone have any other questions about that so far? Okay, so next we're going to load triples related to the first 10 Pokemon. So if you wanted to just filter out, say, the first 10, let's do that. So we create another subgraph again. Here's our namespace that we're going to use called, I think PKM stands for Pokemon probably. So they have Pokédex.data incubator / Pokemon, and we'll call that PKM. And then they also have this namespace called Pokemon here spelled out. And so we just abbreviated both of them. And so now we're going to do a for loop. So for number in range. So this starts at 1 and goes to 10. So we're going to grab the first 10 Pokemon. And then we're going to set Pokemon equal to the Poke number. So that would look like this Pokemon here, and then put the number after it. So we're setting Pokemon equal to that. And then once again, we're using the g.triples to look for those Pokemon. And in this case, we're just looking for a couple of pieces of information. So we want the color, the name, the type, and the label. And we're adding each of those as we go into our subgraph. And so at the end, we should have the first 10 Pokemon and all their colors, names, types, and labels. And we'll print out that there's 85 triples there. And if we wanted to like print out what each one of those things are, we could, but it's just kind of a demonstration that you can do a for loop and kind of filter out this information and create these subsets that you want to work with.
Dan, what is poke again? It's not a namespace, but here, what do you call it?
Yeah, so this is actually just like a normal Python string. And so I used it to create a URI reference based on the number in the range we were using.
Okay.
Yep.
Thanks.
So I was just kind of doing a for loop using the string. Yep. Okay, so now we're going to actually use NetworkX. And remember, NetworkX allows us to deal with graphs in Python. And so NetworkX actually, well, RDFlib has a built-in capabilities to convert an RDF graph into a NetworkX graph, which is awesome because then we don't have to like create a whole new graph from scratch. And it's called RDFlib to NetworkX graph. So we're going to take our graph we had before. And if remember that big old graph, it has 26,562 triples and it's called G. And we're going to make use of that. Here, I can close that down. Okay, so then we're going to create this NX graph, right? Which is NetworkX. So it converted it. And now instead of having how many, remember before what we had is a number of triples, we have nodes and edges. So we've created a graph in NetworkX that has 12,000 nodes and 21,000 edges. And remember, the nodes are kind of the circles and the edges are the lines connecting them. And so we have this very, in my mind, very big graph of information from this Pokédex. So that's how you could automatically convert that RDF we got off the internet of the Pokédex into like a network graph. Let's kind of see how we would use pandas to do something similar. So if we have this Pokemon type CSV, this is maybe a little bit easier to understand than a full Pokédex. We have just a couple of things in here. It's the name, the description, and the Pokemon types. So Pokemon are either 1 or 2 types. So some of them, like Econs down here, is just a poison type. And Spearow is normal and flying type. Or Metapod is just bug type, and Charizard is fire and flying type. So it's either 1 or 2 types. So this is a whole CSV file that has nothing but Pokemon types in it. There's about 1,000 of them in there. So let's use that to, what we're gonna do is use pandas, which is I'm sure some of you are familiar with that, but it's a very nice way to load data that's in a tabular form into what it calls a data frame. So we're gonna read in that CSV, Pokemon types.csv using pandas and create a data frame. And then this dot head just shows us the top part of it. So you can see in a data frame, we have Bulbasaur and it's type grass and poison. Ivysaur is type grass and poison. Venusaur is also, and Charmander and Charmeleon are just type fire. Okay. And then we're gonna create a NetworkX graph from that data frame. And then we'll play around with it a little bit and see what this looks like. So we import NetworkX as NX, and then we do NX from pandas edge list. So for the first graph, we're looking at the data frame we created here and looking at 2 columns, the name and the type 1. And so that'll be this NX type 1 graph. And then notice how some of these have a nan or a no value, not a number for type 2. So these are, we want to filter those out when there isn't a type 2, and then we're going to create another edge list using this filtered data frame. So all we did was drop these NA values, and then we did the same thing and create another graph from the name and type 2 and called it NX type 2 graph. So all we're doing is creating this really large graph that has all the relationships that Bulbasaur is type grass, and then also Bulbasaur is type poison. And so then we compose a new graph using NX compose of the type 1 graph and the type 2 graph. And that refers to the first graph is all the names connected to the type 1, and then the second graph is all the names connected to the type 2, dropping all those NaN values. I don't think we're actually going to add color, so I can probably just remove that line. So then if we print this, there's a graph with 928 nodes and 1,432 edges. So we, once again, took that CSV file with all the information on the names and types and created this NetworkX graph that connects, Bulbasaur is a node and it's connected to an edge to another node called grass, for example. And there's 928 of those nodes, which are all the Pokemon and all the types, and 1,432 edges, which are all the relationships between them. Okay, so the last step, we're going to use pyviz once again to visualize this. So there's a pyviz main thing is called network. So just like NetworkX kind of has NX, this one has a network as well. So we have lots of graphs and networks in our thing from the different libraries, but we're going to create a new network and give it a size 800 pixels. And then we want the width to be 100%. And we also want it to show up in our notebook. Otherwise it would create a new tab. And then we do from NX. We take our NX graph from up here. So pyviz can directly take in this NetworkX graph, and we're gonna, I'll show you what these buttons are, but we're gonna add some physics buttons so we can mess with the graph, and then we want to show the graph. And so now this should load here. And it's gonna take just a second so you can see it loading. And so remember, we're creating this graph of all the relationships between the Pokemon and the types. And so And it has 928 nodes and 1,432 edges. So that's why it's taking a second to load for us. Is there any questions while that loads?
I had a quick one about the compose graph function.
Yeah.
Do you have to have like nodes that are like hashable or have like, or is it solving like graph isomorphism? And I guess like, can that really scale, or do you need to have like hashable nodes or something?
So all it's doing is, so it already had like, say, in this NX, or it already had a NetworkX graph with one edge list, and all it's doing is combining them and saying, hey, I'm adding this number of nodes. And I think NetworkX already knows, like, hey, if I see a node named grass and another node named grass, that those are the same nodes. So I think it's just adding those networks together and assuming the ones with the same, labeled the same, are the same things.
Okay, makes sense.
So what is this doing, everyone? Why does it all look crazy? So it's actually unstable. It's trying to solve itself. So what we can do down here, this is why I have the physics enabled. What this does is has physics on how it solves the graph, and we'll change the solver to say the repulsion one, because this other one doesn't seem to be solving. And if we scroll back up, we can see that it's now solving. And it's going to kind of settle down a little bit. So it's actually solving this, and you can actually mess with the other physics stuff down here. So you could say, I want the central gravity to be different, and you can see the graph will change, right? So it will, you can actually change all these settings and kind of play with the physics of the graph, which is kind of neat to look at. But maybe before we play with that, we can go look at our graph itself.
What exactly do you mean by solving?
So it's, and you can see some of the physics things down here. So there's like springs and spring lengths and damping. And so it's taking all the nodes and edges, and it'll probably be more apparent if I drag on something. So right here, this is for fire types, and I can actually drag it out here.
Like, is it still mapping out all the relationships?
Yeah, it is. All the
Okay.
relationships are there. It's trying to like figure out how to arrange everything. And you could have weights again. Remember, on the edges could have a certain weight. So that could be part of the
Right.
solving as well, that some things should be, I guess, closer, further apart. There's no weights on this information, but it's actually solving all these relationships.
Okay.
So there's a lot of nodes and edges on here, right? But you can see that if you select one of these, so this is all the normal types. And so all these normal types, like Eevee that we were talking about before, is just a normal type, right? It's connected to that. But some of the other Pokemon are connected to multiple types, and you can see like the full graph here of the information. So yeah, there's psychic types down here and fire types, and yeah, it's almost kind of like a lot to look at, isn't it? But you can see all the different, these are all the water type Pokemon.
You're working with the smaller CSV file rather than the Pokedex you'd pulled out before. What happened when you tried looking at the Pokedex?
So to be honest, when I was trying to load the full RDF, it was crashing Jupyter notebooks. And I'm not sure why it was doing that. It shouldn't crash it, but I'm not sure why the full Pokédex wasn't loading. So I decided for a demo anyway, I think it's more interesting looking at something specific, like a subset of the information. So that's why I just took all the types so we could visualize that.
Yeah, because you spent some time pulling out the RDFs and then you didn't use it.
Yeah, that's right. I did want to show though, like, hey, you we actually did create all the RDFs. We created all the graphs and edges and all that stuff, but it was maybe too much information to try to like visually show in a graph, right? So, but it'd still be, imagine if we're connecting information that we want to be able to query and parse, having all that information, say, in a graph database that then you could run queries against and find the information you're looking for and make those connections and answer the questions you have is still really useful, even if, you know, it's not it's not necessarily useful to create a graph of 26,000 nodes or something like that, right?
Well, this is where coloring it helps.
Yeah, we could add some color too. So in the demo, once again, we kind of showed how to add an RDF manually, how to parse n triples RDF, how to load all those triples in, how to select certain pieces of information from an RDF, and then also how to use things like pandas and NetworkX to create graphs, and also pyviz to visualize it. Does anyone have any questions about any of that?
Dan?
I do, but you got one in the chat that was before me.
Okay.
I'm sorry, it's a starter question for me. If it's too down the rabbit hole, I can do my own research on the side. But I know we talked about weights earlier. Is that just like the same as a bit length, depending on the value type, or is it something different?
So like bit length, you're talking about like, hey, this integer can only be so long or something like that. Is that what you mean by that?
Yep, exactly.
So I think this is a little bit different than that, in that you're actually saying one, I guess, how strong the relationship is. So like say a Pokemon was 90% fire type and 10% normal type or something. Pokemon aren't like that. But then you could put a lot more weight on the 90% than the 10%. And so then on the graph, you could show that that relationship is stronger to one type than another.
That makes sense. Thank you.
Yeah. Any other questions, anyone? Was there one more?
Yeah, is network graph and graph database, can those terms be used interchangeably or not quite?
So a network graph is the creation of these relationships between the nodes and edges. That becomes a network graph. And then if you store it in a specific type of database that is meant for rapidly looking up and parsing and querying that information, that would then be in a graph database.
Okay.
So there's like Neo4j and a whole bunch of other graph databases that are optimized for querying that type of information in this form and coming back with results quickly.
So they all have the same underlying concepts.
Yep.
Okay.
They do have sometimes so we were talking about things like Sparkle to do queries. Some of the graph databases have their own language to do queries with. So sometimes the query language is slightly different, but the concept of nodes and edges and connecting network information is all the same.
Thanks.
Yeah, thanks for that, Evan. Any other questions, anyone?
Dan, I have a question on if you try to plot any of these without the physics, is that not useful? I mean, I know that you have spring constants and repulsion and gravitational attraction between nodes. It seems like by applying some of the concepts of physics, it helps to arrange the nodes in a certain way. But if you don't apply that, then what? Or is that a nonsensical question? I mean,
we can turn off physics and see. So if we turn off physics and then drag stuff.
Oh, I see it. I guess, yeah.
So it just and if you solve it without physics, it won't rearrange stuff, right? So it'll just be whatever it'll have all the lines and edges there, but it's not in any type of order that makes sense where you can.
So like the physics helps sort of cluster
Yeah, exactly.
things together and so make associations more apparent, I guess.
Yeah, exactly. Yep.
Right. Yeah.
And we can,
Right.
yeah, there, and then you can use like, there's other solvers. It's kind of fun to, yeah, you can change like your spring constant and make things like more or less damped, right? And you can see how
Right.
your changes affect, I guess, yeah, make it easier or harder to see the information you want, or yeah, get the kind of look you're looking for in the graph, right? So, and sometimes depending on your how damp things are, your spring constant, then it takes it longer to solve because
Cosmology.
yeah, because of physics, I guess. Yeah.
All right, thanks.
Any other questions, anyone? Is everyone excited to go make some network graphs?
It feels less over my head than it did before, so.
Yeah, that's good.
And
Yeah, go ahead.
while you were talking, I kept thinking about blockchains. Is there any kind of correlation between the two, or is that just an illusion in my mind? I can elaborate a little bit. You were
Sure.
talking about information being distributed among different servers. And that's, my very simple understanding of blockchains is that information is also distributed among different servers. So that was the starting point for my question.
I'm sure there's someone online who's like a blockchain expert, but I understand blockchain's built on a ledger that's a distributed ledger. So I think blockchain gives you this ledger of information that that is distributed, but I think what's not similar is kind of these nodes and edges and connecting the information in this kind of graph network form. So I think the distribution of information is maybe similar.
But that's about it.
Yeah, maybe that's my thought. Yeah.
Okay, thank you.
Yeah.